Buddy, this is Noah, and I am going to go over applications of function operations. This is going to be a pretty straightforward, simple function operations that we can see when we have an application and we have a function for a given scenario, and we're comparing that function to similar functions of other slightly different scenarios. So let's get into this example where we have a car driving 60 miles an hour when the timer starts at mile marker 0. So at time 0, this car is going 60 miles an hour through mile marker 0, driving, we're assuming, in a straight line, going 60 miles an hour, nothing in its way, staying at 60 miles an hour. So suppose further that it maintains this speed. We're going to start by just determining the function d, outputting the distance traveled after t hours since the car has crossed the mile marker 0. So this is going to be pretty straightforward. The distance is going to be simply the distance as a function of t, so capital D of t equals 60 miles per hour. So that's 60 times t, where t is in hours. Let's make sure we understand. T is time in hours, and d of t, the distance, is the distance traveled after t hours. All right. So that's our original situation that we're going to have as our baseline. We're now going to look at a new scenario. We have a second car also going 60 miles an hour. But this car is at mile marker 5 when the timer starts. So do we not want to describe the distance this car has traveled in terms of d from the first car? So the second car, so we'll call this d2 for the second car. This second distance is also a function of t. And this is going to be the same distance as the first car, except for it's 5 miles ahead. It's 60t plus 5, right? And instead of writing the whole thing out like that, we are just going to write it as d2 of t equals d of t plus 5. It's the original distance, simply adding 5 miles onto it. Distance traveled by the first car is d of t. And then, but 5 miles ahead. So we do that plus 5 for that. Okay, so that's one example of a function operation. We're adding 5 to the original function to say that the second car is got the same kind of distance as the first car, but just 5 miles ahead. That's a pretty simple scenario where we could be doing this. We have a third car now for part C, and this is going half the speed of the first car, and it crosses the mile marker 0 at the same start time as the original car. And we want to now describe this distance, the car that this we now want to describe the distance that this car has traveled in terms of the distance the original car has traveled. So this is d3 of t, and it's going to be like the distance of the first car, but it's going to be going half as fast. So what we do is we put a 1/2 t in here. The way that we can interpret this is the idea that, if it's going half as fast, then say after 1 hour, this car should only have gone 30 miles instead of 60 miles, right? And so that's like, we should know that the distance for this third car is 30t. And this is the same thing as 60 times 1/2 t. So this is d of 1/2 t, right? We're plugging the 1/2 t in for the t in the original distance equation. we can think that the second car's distance traveled is going to be it's going to be half that of the original car, but we're interpreting it as terms of speed, not half the distance. So because it says that it's half the speed, I want to think of it as this car has traveled like half the amount of time as the original car. Because the speed is half that of the original car, its distance is always going to be able to be calculated by saying it's as if the first car had gone for half as much time as it had originally. And so that's how we're able to work this in here. And really pay attention to that. Think about that when you do the now you try problem. That's probably the trickiest one of all of them that we're going to do right now. All right, we now have a fourth car. And it's going the same speed as the original car, but it crosses the mile marker, mile marker 0 1/2 hour after the first car. So the time is a half hour delayed, right? So it's a half hour after the first car. So this distance sub 4 for the fourth car as a function of time is going to be the same distance as the first car, because it's going the same speed, but the time is delayed by a half an hour. We can take the time and subtract a half an hour from it, and then that will give us the distance for this new car. And if we took that and we plugged it in to the distance formula for the original car, which was 60 times t, we get 60 times t minus 1/2. And that would be a nice way of expressing the distance this fourth car is going. We could also simplify that to 60t minus 30, and we can see that it is 30 miles behind the original car because of its half-hour delay in getting going. So that one I think is a little bit nicer for the input when we're inputting something into the original function to kind of interpret how that's working. Now we have a fifth and final car crossing mile marker 0 at the same time as the original car, but the distance is always 1.5 times that of the original car. So this is like multiplying the distance. And it's 1.5 times, that's 3 halves. 1 and a half equals 3 halves the distance of the original car. So we can say that the distance of the fifth car is always going to equal 3 halves times the distance of the original car. If we simplified this, we'd get 3 halves times 60t, and if we simplify that, the 60 divided by 2 is 30, times 3 is 90t. 60 is over 1, so I can reduce the 2 to a 1 and the 60 to a 30, like that. When we're multiplying fractions, it's always nice to reduce before multiplying, because reducing shrinks the numbers down, multiplying makes them bigger. If we multiply first, we get bigger numbers and then have to make them smaller again. If we make them smaller first before making them bigger, it's going to make the arithmetic a little bit easier. Right. So these are some simple applications of how we can interpret applications to compare, at least in this case, distances of different cars and how they're in similar scenarios but not quite the same, and how their distances are related but not equal. All right, go ahead and take your notes on that, rewind, fast forward, pause as you need to, and then move on and do the now you try problem. And once you've given that a go ahead and watch the next video where I'll walk you through that. And that'll be it for this module 2b. Thanks again for watching. I'll see you shortly.